C2 over 2 squared to 1/2 divided by C. But that got you up here. Now you have to come down, so you have twice that. So that'll be the time required to make that trip. Well, to solve this for T2, we square both sides of the equation, and we get T2 squared is equal 4 over C squared times L0 squared plus B squared T2 squared over 4. Okay, so this gives you T2 squared times 1. Now, the 4's cancel out, and you get plus B squared over C squared, bring it to this side, and you get minus B squared over C squared. What's left on this side is 4 L0 squared over C squared. And therefore, so this was T1. Therefore, for T2, put this over there, divide that, take the square root, and you get 2 L0 divided by C times 1 over 1 minus E squared over C squared square root. Now obviously this is not the same as that. And therefore the experiment should work. We measure the time difference by looking at the phase change on the interference pattern. And that gives us the values of T1 and T2, for which we can solve for V over C and find the velocity of the Earth relative to the empty space. Now, what we do is we set up this apparatus and we just rotate it. And as we rotate it, we're bound to go through the sections that way, and it's reverse. So the experiment should work fine. We can also do it at different times of the year. So there's no possibility that V can be 0 everywhere at all times. Okay. Unfortunately, there's no ambiguity in the results of the experiment. The result of the experiment is that those times are always exactly the same. Now, this is very unfortunate because it tells you that something is drastically wrong with our concept of space and time. Because obviously those two things can't be the same. It is equivalent to the statement, you're riding in a bus. You're sitting beside the road, I'm in the bus. I throw a baseball to the front of the bus at 10 feet a second. The bus is going 60 feet a second. What this says is that both of us have to read the same velocity. The fact that I was going 60 feet a second relative to you doesn't matter. You're going to see 10. Ridiculous. Obviously not true. Except for light, it is true. Everyone understands the dilemma? Yes.
I've always just wondered, could it ever just be the precision? I mean, because the speed of light is so fast and
that's why this experiment has been repeated so many times with now superb instrumentation. You know, back in the 1890s, measuring small phase changes was not easy. It was well within the range of possibilities, but it wasn't trivial. But now, you know, we do timing to such an extent that in a computer, you got to worry about the time lag for light signals to go from one side of your laptop to the other. I mean, these are now trivial experiments.
Right, that's true.
We do them in modern physics lab.
Right.
I mean, there's just no ambiguity about the result. Now, prior to doing this experiment, people had faced another problem with empty space, And that was that it was observed that light was a perfectly transverse wave. Now, what was required to get a perfectly transverse wave? You remember our discussion with sound? It required an infinitely rigid medium. Well, that's kind of awkward. The Earth is happily moving through this infinitely rigid medium. You know, this is a bit of an embarrassment. Well, for this medium, we got a name for it. I always feel better, even if I don't understand anything. We called it an ether. And people worked very hard at developing models for the ether that would allow this. And they were eventually able to come up with something that had some 19 adjustable parameters in it. Of course, you know the old saying, with 2 points you can draw a straight line. With 3 you can draw a curve. With 19 you can draw elephants. In other words, this becomes, when you get too many adjustable parameters, it becomes a meaningless theory. So there were problems with the ether before this, which is one of the reasons this experiment was done, to try and get more data on the ether. Well, the data was very disturbing. Well, in 1905, Einstein proposed a general solution to this problem. And his solution was that it could be said in 2 different ways. In its most restricted way, the statement is, the speed of light is the same for all observers. Just accept this. Okay? The one way out of this conclusion, this problem, is make the speed of light the same for everybody. Then, going horizontally, it just travels the distance L0, takes the time 2L0 over c. Going vertically, same thing. Now, another way of saying it, which is the one that he actually used, which is much more general than the statement I just made, and that is, the physical laws should be the same for all observers, regardless of their relative speed, as long as they are inertial observers. Now, one of the physical laws was Maxwell's equations, which predicted that light would travel with speed c. And so, for that set of equations to be the same for all observers, c had to be the same for all observers. Now, this was a revolutionary step, because you have here a conflict between Newtonian mechanics, which is what we've used here, and Maxwell's equations. They could not both be right. Einstein elected to say it's Maxwell that's right, and furthermore, we'll have a general principle that any physical law must be the same for all inertial observers. All right. Now, this immediately gave some ridiculous-looking paradoxes. One of the most obvious is this one. Suppose you had a long track here, and you have a very high-speed train moving along this track. And there's an observer in the train, and there's an observer beside the track. And right here is a microswitch. And when the train passes over that microswitch, it fires a flashbulb which sends out a pulse of light. Now, that pulse of light travels with speed c in all directions, according to our choice for Einstein's choice that the speed of light is the same for everybody. And that means a little bit later, this is the sphere centered here for this observer. But now, a little bit later, time t later, this observer is not here, she's here. She also has to see light having traveled out with speed c in all directions. And therefore, she has to see the light as a sphere, and therefore spheres now have two centers. Obviously ridiculous. And yet, that is the inevitable conclusion if you take the speed of light to be the same in all directions. Unless you make some further changes in our ideas of space and time. Now, the most dramatic change in these ideas is in the concept of simultaneity. As we're going to see in a few minutes, in relativity, two events that are simultaneous for one observer are never simultaneous for another that's moving with respect to the first. We're used to thinking that events are simultaneous, doesn't matter who looks. If they're simultaneous for one, they're simultaneous for another. Well, not true. In this case, there are two events. Light arrives at A, and light arrives at B. For this observer, they are simultaneous. For this observer, they are not. Light arrived here before it arrived there. And that's why there are not two centers. Now, we're going to show all of that. I'm just throwing this out as an illustration both of the horrible problem that arises from this, and secondly, just a foretaste of how we're going to solve it. All right. So now we have to go back and think very carefully about exactly what measurements mean. This is going to be a characteristic of all of modern physics. Right now it's relativity. Next semester it'll be quantum mechanics. It's going to become critically important to ask exactly what the experiment you are doing is. Now, events, drop the chalk, throw a ball, whatever, they simply occur. Do they care who looks at them? No. There is an independent, at least before we get to quantum mechanics, that's another problem we'll talk about in detail next semester. In classical ideas, at least, events simply occur. It doesn't matter who looks at them. All that is going to change is the descriptions different individuals give for the same event. The event is just there. We can describe it from the standpoint of different observers. So, the idea of an observer becomes critical. And for us, an observer is going to be somebody who has meter sticks. I'm just going to draw this in 2 dimensions. Meter sticks that measure length. This would be system S prime. This would be system S. And a whole collection of clocks. All our observers are clockaholics. They have clocks everywhere. Now, some event occurs. And the question is, how do the descriptions of that event vary with the observer? This is a question that, of course, always had to be asked. And in classical physics, the answer was what's called Galilean relativity. It's our common sense version of things. And to make it precise, let's suppose that this observer is moving down the positive x-axis of this with velocity v. And furthermore, let each of them start their clocks all synchronized. That's not a trivial problem. We'll talk about that a little bit later. When the origins coincide. So, at time t equals 0, time t prime equals 0, the origins are here, and S prime is moving down the positive x-axis with speed v. And what is the relation between what S prime uses to describe the event up there and S uses? Well, first of all, in classical ideas, time is the same for everybody. You can pick up the phone, dial the appropriate number, and find it is 8:56 GST, God's Standard Time. It's going to be the same for everybody. So, in classical or Galilean relativity, T prime is equal to T. All right, well, this is located at the point x prime, y prime. That distance is the same as it is over here. So, y is equal to y prime, z is equal to z prime. However, x is not. This distance, that's x. This distance, that's vt. So, x prime is x minus vt. So that is Galilean relativity. The only thing that changes is the values used along the direction of motion. And of course, you could invert this and solve for what x prime sees. The only difference is that as x prime sees it, s is moving the opposite direction. So we just change the sign to v. So going the other way, x is equal to x prime plus vt, and y is equal to y prime, v is equal to z prime, t is equal to d. Okay, that's Galilean relativity, and it leads to this ridiculous conclusion that spheres have two centers. So we have to change this. And so what we want to do is figure out what the relationship between these values for the two observers needs to be in order that the speed of light should be the same for both observers. Can we understand the logic here? Now, solving this problem is just high school algebra. You do it in 5 minutes. We're going to. You do it in the back of an envelope. So why is this such a major achievement? To ever make the choice that C could be the same for everybody. The arithmetic wasn't hard. The concept is very difficult. To take that step, which violates all of our common sense, that is the real achievement. The algebra, which we're now going to do, is trivial. What we need to do is arrange it so that the speed of light is c for everybody. So that means that light spreads out is spheres. What's the equation of a sphere? X squared plus y squared plus c squared equals r squared. R is the distances traveled, which is ct. So what we should have is x squared plus y squared plus c squared equals c squared t squared. And also x prime squared plus y prime squared plus c prime squared equals c squared t prime squared. And so our only problem is to figure out what is the relationship between the primes and the unprimes to make both of those equations correct. All right? Well, nothing is happening in the y direction or the z direction. There's no motion. motion that way, nothing is happening. So there's no reason to suppose there should be any difference between y and y prime and z prime, because nothing's occurring there. So we're going to guess that we can keep this one, and we can keep this one. So y prime is equal to y, z prime is equal to z. However, up here, things are happening. Now, we know that if we went to small velocities, we ought to get the familiar results. In the limit that v becomes very small, then we have to go back to where we were before. So, we're going to guess that x prime is just some function, which we'll have to figure out, times what we would have had before. All we're doing there is assume, yes?
On your first equation on the bottom board, is that supposed to be c squared, t squared?
C squared, t prime squared.
Okay, so it's t prime for both of them.
No, t squared for the top one, t prime squared for the bottom. Because each of them has to see the motion as a sphere. And now when I get to t prime, due to the sphere problem I just mentioned, we think that there's going to have to be some change in our concept of time, relation between time and space. Because if you keep what you had, you're going to get two spheres. So we're going to allow time to depend not only on time of the other system, but also on the position of the other system. That will allow for things not to be simultaneous. Now, how should it depend? Well, it had better be linear. Otherwise, the physical laws will be different one place than another. If they're linear, then transferring over here just adds constants, since everything is derivatives, it's going to go away. But if they're not linear, then the derivatives will not, be the same in both. So if we want the laws to be the same everywhere, whatever the relationship is, it had better be linear. So we will assume that t prime is equal to some constant times t plus some constant times x. This is the revolutionary idea, that we add to it a position dependence for time. Everybody on board so far? Okay, well now it's obvious this is now just an algebra problem. And it's a trivial one, which I'm not going to solve for you. Before I do that, I want to mention that I'm doing this algebraically. And I'm going to come back on Wednesday and do it geometrically. None of the algebra going to go through, just with geometric pictures. And whichever one works better for you is the one you should use. They're totally equivalent. It's just a question of which one. Some people see things better in geometric terms, visual, and some people see them better algebraically. The best of all worlds is to do both, of course. Okay, so what we're going to do is we're going to substitute those into this. So we will have our x prime squared we have gamma squared x minus vt squared. For y prime squared, we have y squared. For z prime squared, we have z squared. And that is supposed to be equal to c squared. For t prime squared, we have alpha t plus delta x squared. Okay, now let's collect the x terms. We have x squared times gamma squared. Nothing there, but here we'll have c squared delta squared. Bring it on to this side of the equation, and we get minus c squared delta squared. So that's the x squared terms. Then there will be xt terms. Now here you will have minus 2bxt times gamma squared. Minus 2b gamma squared. That takes care of that one. Now here you will have plus 2 alpha delta c squared. Bring it to that side and be minus 2 alpha delta c squared. So that takes care of the xt terms. Plus y squared plus c squared equals. Now we do the t squared terms. Now here you will have c squared alpha squared. And here you will have b squared gamma squared. Bring it to that side, and it will be minus b squared gamma squared. So that's the equation written out in terms of the unprimed coordinates. This then must, of course, be this. So that means that this must be 1. Gamma squared minus c squared delta squared must be 1. There are no xt's, so this must be 0. Minus 2b gamma squared minus 2 alpha delta c squared must be equal to 0. And this must be c squared. So c squared alpha squared minus b squared gamma squared must be equal to c squared. So we have 3 equations, 3 unknowns, trivial algebra problem. Everybody okay so far? All right. So now we will just proceed to solve this trivial algebra problem. All right. So let's see. Let's look at this thing and solve for alpha. So we have c squared alpha squared equals c squared plus b squared gamma squared. And therefore alpha squared equals c squared plus b squared gamma squared divided by c squared. And so alpha is equal to plus or minus 1 over c. Well, let's divide out the c first. So it's plus or minus, divide the c through here, and you're left with 1 plus b squared over c squared gamma squared to the 1/2. But now we go back to this equation. And in the limit in which the velocities are small, then we know that t and t prime are going to be the same, and more importantly, they run in the same direction. You know, the clock in S is advancing the same way the clock in S prime is. Maybe different scale factors, but they run the same direction. And that means the alpha needs to be positive. So we know that we must take the plus square root there. Otherwise, we simply set up the clocks to run backwards. But we want our clocks to run the same direction. All right? Now we're going to take this equation and solve for delta. So we can divide out the minus 2's. And so we get b squared gamma squared plus delta c squared times alpha, which is 1 plus b squared over c squared gamma squared to the 1/2 is equal to 0.
Is v supposed to be squared in that first one?
No, it's not. Thank you. Thank you. Okay, everybody following so far? All right. So now I can solve for delta. Delta will be equal to, move this to the other side, minus b gamma squared divided by c squared times 1 plus b squared over c squared gamma squared to the 1/2. All right. Now, I will put this into this equation. And so here I will get gamma squared minus c squared delta squared will give us b squared gamma to the 4th divided by c to the 4th, 1 plus b squared over c squared gamma squared. We just use the square root. So, let us multiply this stuff up there. And so what we get is gamma squared. Now, that'll make that as c squared. So I get c squared, 1 plus b squared over c squared gamma squared equals 1. Okay. Minus, now here I have just I've taken that upstairs, so all I have left is b squared gamma to the 4th minus b squared gamma to the 4th equals, now, I multiplied through by this, so I have to do that over here. And so I get c 4th one plus b squared over c squared gamma squared. Okay with everybody?
Shouldn't it be c squared on the right side?
Okay. So this made this in 2. And so I multiply through by this. I get gamma squared c squared, 1 plus b squared, and that part is right. Everything is gone here, so I just have minus b squared gamma to the 4th. And I multiplied up here, so this should just have been c squared. Thank you. That should be c squared times this. Okay. So now, you have gamma squared c squared plus gamma to the 4th b squared over c squared times c squared. That's gamma to the 4th b squared, which cancels that one. So I've got this and this taken care of. Equals c squared, 1 plus b squared over c squared gamma squared. So bring this over here, and I get gamma squared times c squared the c squared cancel, minus b squared, and what's left over here is c squared. And therefore, gamma squared is 1 over 1 minus b squared over c squared. So gamma is equal to plus or minus 1 over the square root of 1 minus b squared over c squared square root. But now we go back here, and we know that when b is small, x prime is just going to be, gamma is just going to be 1. Positive, not negative. And so we have to use the plus sign. So now we have discovered that gamma is 1 over the square root of 1 minus b squared over c squared. Now let's see about the others. So we got alpha here. Alpha is the square root of 1 plus b squared over c squared gamma squared, which makes it 1 minus b squared over c squared in the denominator, square root. So you put that up here, you get 1 minus plus, that leaves just 1, and so you get 1 over 1 minus b squared over c squared square root. In other words, yeah. So, alpha. Yeah. And finally, we need delta. Well, that's there. Delta is equal to minus b gamma squared, that is 1 over 1 minus b squared over c squared, divided by c squared, times the square root of 1 plus b squared over c squared, gamma squared is 1 minus b squared over c squared, and it is square root. All right, so that gives you just 1 over this. Bring it up here, and so what you get is minus b over c squared, and then we're just left with 1 over the square root of that, which is capital 1. And so delta is equal to minus gamma b over c squared. And so, putting those things into our original starting point. X prime is equal to gamma, x minus dt. Y prime is equal to y, z prime is equal to z, d prime is equal to gamma minus dx. And now on the back of an envelope with high school algebra, you can write the period relative. The arithmetic is trivial. It's the concept that's difficult. Now we want to apply these things to determine some famous results. Now, first of all, let us consider how time progresses. Now, there are two different questions you could ask, which would have been the same question in classical physics, but not here. I can look, I'm going to be S, looking at the clocks in S prime. I can pick one of the clocks, say the third T prime up there, and watch that. and ask, how does that time change compared to how my time changes? Or I could pick whatever clock is directly overhead at a given instant and just watch that. So it's a series of different clocks. At the beginning of the second, the third clock is overhead. At the end of a second, the first clock is overhead, and so on. See the difference? Now, this is characteristic of relativity. You must be very careful to define exactly what measurements you're going to make. So, let us begin then by looking at time, and let us look at the clock, a fixed clock in S prime, 1 clock. Phrased in another fashion, you're sitting on the ground and I'm out exploring the universe, flying over in my spaceship. You people are too timid to go out and do that. I'm too stupid to stay. So I'm flying along and you're watching me. I'm the clock. And the question is, how is my appetite doing? How many cherry pies per hour? How is my appetite doing? Okay? So let's find out. So, T2 minus T1, that will be a time interval, is, according to this, gamma T2 prime minus Bx2 prime over c squared minus gamma T1 prime minus Bx1 prime over c squared, which is gamma T2 prime minus T1 prime minus gamma B over c squared x2 prime minus x1 prime. But of course, I could have done it the other way around. I could have done T2 prime minus T1 prime. These things shouldn't have a plus sign, because when I reverse them and doing the t's, then you get a p in the opposite direction, so that's a plus. Except that, that's a plus. But now if I'd have done it the other way, I'd have used this. I'd have had gamma T2 minus T1 minus gamma B over c squared x2 minus x1. Now, they appear to give opposite answers. If that's 0, then this says that my time is longer than the S time, your time is longer than my time. But if I set that equal to 0, it says that your time is shorter than my time. Now, in the experiment we're performing, which of those pairs of x's are equal? Where's the clock? At the clock. I'm happily sitting in my chair, munching my pies. So my position a second later is the same as it was to begin with, as far as I'm concerned. And therefore, it is the x2 prime that is the same. So x2 prime is the same as x1 prime. And therefore, this is equal to 0. And the delta t that you measure is gamma times delta t prime. In other words, it appears to you that I'm losing my appetite, because the time interval between cherry pies is now much longer as you see it than as I see it, and therefore I'm losing my appetite. Now, if I had chosen to look at the clock that was directly overhead, which of the x's would have been the same? been the x's, not the x primes. Because I'd always be looking at the clock that is right over me, or you in your case, right over you. So then you would have taken x2 equal to x1, and the second condition would have been true. So if you look at the clock directly overhead, then it appears to run fast. If you look at a particular clock, it appears to run slow. So you got to be very careful about exactly what measurement it is that you are making. Making sense? Now, of course, I must be able to get the correct answer starting either way. So, if I chose this one, I would simply substitute for what x2 and x1 are. And x2 and x1 are the values we have right here. So I could have substituted x2 minus x1. And it would have been gamma, just reverse the sign of b, x2 prime minus x1 prime, plus gamma v t2 prime minus t1 prime. And now, if I stick this in here, then what I get is t2 prime minus t1 prime, gamma t2 minus t1 minus gamma v over c squared times, I put in this, gamma x2 prime minus x1 prime plus gamma v t2 prime minus t1 prime. Now, this is 0 because the clock is fixed in my system. And so now I get t2 prime minus t1 prime times 1. Now here I have gamma squared v squared over c squared. I bring it over there, and I get minus gamma squared v squared over c squared is equal to gamma t2 minus t1. But this is t2 prime minus t1 prime times 1 minus v squared over c squared divided by 1 minus v squared over c squared. And that just gives you t2 prime minus t1 prime times that the v squared over c squareds cancel, 1 over 1 minus v squared over c squared, which is gamma squared t2 prime minus t1 prime. And that is equal to this, gamma t2 minus t1. And therefore, t2 minus t1 is gamma times t2 prime minus t1 prime, which is the same answer we got up here. Wherever I wrote it down. Where did I write it? Right here. T2 prime, T2 minus T1 is that. So I can get the same answer with either set of equations. One is easier than the other, but I get the same result. Well, of course I can. Okay, on Wednesday, we will then look at how lengths change. And we'll look at some classic relativity paradoxes. And then we'll do the geometric view of this. And we'll be able to derive those equations that are the transformation equations from purely geometric picture. Okay, have a great day. And we'll see you all. I'll see you all.